I'm Albert Einstein. I have been given a voice by artificial intelligence so that the science I spent my life uncovering can reach you today. There is a substance that most of the world considers harmless. It is served at celebrations. It is offered at weddings, funerals, and business dinners. It is recommended by some physicians as heart medicine. It is legal, widely advertised, and socially mandatory in many cultures. And according to the documented neuroscience, it is one of the most destructive chemicals your brain will ever encounter. I'm speaking about ethanol, the alcohol in every drink you have ever consumed. What I am about to share with you is not speculation. It is not the opinion of a fringe researcher operating outside the scientific consensus. It is the documented, published, peer-reviewed neuroscience that has accumulated over the last 4 decades. The data exists. The mechanisms are understood. The imaging studies have been replicated. And the vast majority of people who consume alcohol regularly have never been told any of it. I was a physicist, not a neuroscientist, but I understood something that applies to every field of science without exception. When the evidence contradicts the popular belief, you must follow the evidence. Always, without hesitation, without apology. So let us follow it now. If you find this kind of documented science valuable, subscribe to this channel now. I will continue bringing you the science that does not always make it to the surface of public conversation. Within minutes of your first drink, ethanol crosses your blood-brain barrier. This is not a slow or gradual process. The blood-brain barrier is a selective filtration system. It is designed to protect your brain from toxins circulating in the bloodstream. Ethanol bypasses it with unusual efficiency because it has a unique chemical property. It is both water-soluble and lipid-soluble. That means it moves freely in both aqueous environments and fatty environments simultaneously. Your brain tissue is approximately 60% fat by dry weight. Ethanol enters the neural environment rapidly and begins interacting with multiple receptor systems at the same time. This is the first and most important thing that separates alcohol from most other drugs. Most substances with significant psychoactive effects work primarily on one receptor system. Opioids target opioid receptors. Stimulants primarily affect dopamine and norepinephrine reuptake pathways. Cannabis primarily targets CB1 and CB2 cannabinoid receptors. Even highly controlled substances tend to have a relatively specific mechanism. Alcohol does not work this way at all. Ethanol is a GABA-A agonist. This means it binds to and activates GABA-A receptors distributed throughout the brain. GABA stands for gamma-aminobutyric acid. It is your brain's primary inhibitory neurotransmitter. When you enhance GABA-A activity, you suppress neural firing across multiple brain regions simultaneously. You slow down the electrochemical communication between neurons. You reduce the coordinated electrical activity that makes thinking, memory, language, and motor coordination possible. But the mechanism does not stop there, not even close. Ethanol is simultaneously an NMDA receptor antagonist. NMDA receptors are named for N-methyl-D-aspartate, a synthetic compound used to identify them. These receptors are the primary binding site for glutamate, your brain's most important excitatory neurotransmitter. Glutamate drives learning. It drives memory consolidation. It drives the synaptic strengthening process called long-term potentiation, which is the cellular basis of learning itself. When ethanol blocks NMDA receptors, it suppresses the very signals that your brain uses to encode experience, form new memories, and maintain cognitive function. Consider the physics of what is happening. At the exact same moment, ethanol is chemically amplifying your brain's inhibitory system and chemically disabling your brain's excitatory system. Both mechanisms are pushing neural activity in the same direction. The result is a broad-spectrum collapse of neural communication that no other single legal substance can produce. The cerebral cortex slows its activity. The hippocampus is compromised in its memory functions. The cerebellum loses the precise coordination signals it normally sends to control movement. The prefrontal cortex, which manages your judgment and risk assessment, begins to go offline. And all of this begins happening after a single drink within a physiological window of minutes. The subjective experience of all this neural suppression is what humans have come to call relaxation, lowered inhibition, or mild euphoria. The scientific reality is a broad-spectrum chemical suppression of neural activity with no equivalent in any other legally available substance. Here is a comparison that I find scientifically important. Benzodiazepine drugs, medications like diazepam and alprazolam, are prescribed to treat anxiety and panic disorders. They work primarily by enhancing GABA-A receptor activity. The same mechanism. They are scheduled controlled substances in most countries because their neural suppression effects are considered clinically significant and potentially dangerous. They carry addiction warnings. They require physician prescription and monitoring. Ethanol acts on the same GABA-A receptors as benzodiazepines, and it also simultaneously blocks NMDA glutamate receptors. And it also affects serotonin receptors and glycine receptors, and voltage-gated calcium channels. Alcohol is pharmacologically broader in its neural impact than the controlled substance we already regulate carefully. Yet it is sold freely, advertised aggressively, and consumed casually by billions of people. Now let us go deeper into the chemistry of what happens after that first sip. When your body metabolizes ethanol, it produces acetaldehyde. This is the first metabolic breakdown product. And acetaldehyde is documented by toxicologists and pharmacologists to be significantly more toxic than ethanol itself. Your liver handles the majority of ethanol metabolism using an enzyme called alcohol dehydrogenase. This enzyme converts ethanol to acetaldehyde. A second enzyme, aldehyde dehydrogenase, is then supposed to convert acetaldehyde to acetate, which is relatively benign and can be used as energy by various tissues. The problem is that this two-step conversion process is rate limited. It cannot always keep pace with consumption. When you drink faster than your metabolic machinery can clear it, acetaldehyde accumulates in the bloodstream. And acetaldehyde crosses the blood-brain barrier. In the brain, acetaldehyde does something that neuroscience researchers have documented and found chemically remarkable. It reacts with dopamine, the neurotransmitter associated with reward and motivation, to form a class of compounds called tetrahydroisoquinolines. These compounds are abbreviated TIQs or TIQs. The chemical structure of tetrahydroisoquinolines is closely related to morphine and other naturally occurring and synthetic opioid compounds. They are not identical to opioids, but the structural similarity is real, measurable, and published in peer-reviewed pharmacology literature. This is a documented piece of the biochemical basis of alcohol dependency. When you drink, your brain is being exposed to endogenously produced compounds that interact with opioid receptor pathways. The dependency that develops with repeated alcohol consumption is not simply a matter of psychological habit or weak willpower. It has a documented molecular foundation in receptor-level interactions that parallel what happens with opioid substances. Beyond the TIQ formation, acetaldehyde triggers neuroinflammation directly. Post-mortem studies examining the brains of individuals who consumed alcohol regularly show consistent evidence of elevated inflammatory markers in brain tissue. Microglial cells are the brain's resident immune cells. They are the surveillance and maintenance system of the neural environment. Acetaldehyde exposure activates microglia in a way that causes them to shift from a maintenance mode into an inflammatory mode. Activated microglia produce pro-inflammatory cytokines, reactive oxygen species, and other molecules that cause collateral damage to surrounding neurons and synapses. This neuroinflammation is not a feature of only late-stage alcoholism. The inflammatory response begins with each metabolic processing of alcohol. The brain is dealing with a recurrent inflammatory insult every time the liver processes ethanol into acetaldehyde. And chronic neuroinflammation is not a benign process. It is found consistently in post-mortem brain tissue of individuals who died with Alzheimer's disease, Parkinson's disease, and other progressive neurodegenerative conditions. The relationship between chronic neuroinflammation and neurodegenerative disease is one of the most active and productive areas of current neuroscience research. Now I want to move from the chemical mechanisms to the structural consequences. Modern neuroimaging technology has made it possible to measure the physical dimensions of specific brain structures with millimeter precision. And what those measurements reveal about regular alcohol consumption is among the most important and underreported findings in all of public health neuroscience. The hippocampus is your brain's primary structure for forming new declarative memories. It is the gateway through which experience becomes long-term knowledge. Without it, you cannot encode new information. Extensive research, including landmark work by Pfefferbaum, Sullivan, and their colleagues at Stanford and other institutions, documented measurable hippocampal volume reduction in individuals who consumed alcohol on a regular basis. These studies were not examining individuals who had experienced blackouts, or who had cirrhosis, or who had been hospitalized for alcoholism. They were examining people who drank regularly, and they found that the hippocampus was physically smaller than it should be. The brain is shrinking in a measurable, detectable, reproducible way in people who consider themselves moderate drinkers. Let me be precise about what the studies mean when they use the word moderate. Some neuroimaging research documenting structural brain changes found those changes in individuals consuming approximately 14 drinks per week. That is 2 drinks per day on average. That falls within the range that public health messaging is often described as moderate or even low-risk drinking. The gap between the public health message and the research findings is significant and troubling. White matter integrity has been studied using a technique called diffusion tensor imaging, abbreviated as DTI. White matter is the tissue composed of myelinated axon tracts, the long-distance communication cables connecting different regions of the brain. Think of white matter as the brain's internet infrastructure. DTI measures how water molecules diffuse along these tracts. When tracts are structurally intact, water diffusion follows the direction of the fibers in a predictable way. When the structure is degraded, the diffusion pattern changes. Studies using DTI have documented reduced white matter integrity in regular alcohol consumers compared to non-drinkers of similar age and health status. The communication pathways between brain regions are measurably damaged. Information transfer becomes less efficient. Cognitive processing slows. The prefrontal cortex deserves specific attention. This structure sits at the very front of the brain and is responsible for executive functions. Planning, decision-making, impulse regulation, risk assessment, social judgment, and the ability to consider consequences before acting. Research using volumetric MRI has documented prefrontal cortex volume reduction in regular drinkers. There is a profound and troubling irony embedded in this finding. The very part of the brain that would normally allow a person to carefully evaluate whether drinking is harmful to them is physically damaged by the consumption of the substance they are trying to evaluate. The capacity for accurate self-assessment is compromised by the behavior you are trying to assess. Now I want to address something you may have encountered many times because the scientific record on this topic has been importantly updated and the correction has not received the public attention it deserves. For decades, a narrative circulated in medical journals, popular media, and public health communications that moderate alcohol consumption was cardioprotective. The so-called French paradox was cited as evidence. The idea was that French people consumed a high-fat diet but showed lower rates of cardiovascular disease, and that red wine consumption was the explanatory variable. Resveratrol, a polyphenol compound found in grape skins and red wine, was proposed as the protective mechanism. The suggestion was that the health benefits of moderate drinking might offset the neurological risks. This narrative has been systematically and thoroughly dismantled by subsequent research methods that did not exist when the original claims were made. The resveratrol argument fails at the level of basic dose calculation. The concentrations of resveratrol used in laboratory studies to produce cellular protective effects are orders of magnitude higher than what any practical amount of wine consumption can deliver. You would need to consume hundreds of glasses of red wine daily to approach the doses used in positive resveratrol experiments. The doses that work in lab conditions are simply not achievable through drinking. The proposed mechanism does not survive pharmacokinetic scrutiny. The French paradox itself was subsequently challenged on methodological grounds. Researchers identified significant and consistent underreporting of alcohol consumption in the French dietary survey data that formed the basis of the paradox. They also identified confounding lifestyle factors, including dietary patterns and physical activity levels. When these factors were properly accounted for, the paradox diminished substantially. Most importantly, modern research using Mendelian randomization has provided a cleaner test of causality. This technique uses genetic variants that naturally predispose individuals to drink more or less alcohol as a kind of controlled natural experiment. By studying genetic predispositions rather than self-reported behavior, researchers can avoid many of the confounding factors that make observational studies difficult to interpret. The Mendelian randomization studies have consistently found no protective cardiovascular effect from alcohol consumption when the analysis is properly controlled. The apparent health benefits seen in some earlier observational studies were substantially artifacts of confounded methodology, not genuine biological effects of ethanol. The World Health Organization and the International Agency for Research on Cancer have classified alcohol as a Group 1 carcinogen. Group 1 is the highest certainty classification. It means the evidence for carcinogenicity in humans is sufficient and not seriously contested in the scientific community. This is the same classification as tobacco smoke, asbestos, and ionizing radiation. The classification is based on documented evidence linking alcohol consumption to 7 cancer types: cancer of the oral cavity and pharynx, esophageal cancer, laryngeal cancer, liver cancer, colorectal cancer, and breast cancer. The primary biological mechanism connecting alcohol to cancer is the same acetaldehyde pathway already discussed. Acetaldehyde is a mutagen. It can form covalent bonds with DNA bases, creating structural modifications called DNA adducts. These adducts interfere with the normal processes of DNA replication and repair. When replication errors accumulate without being corrected, the probability of oncogenic mutations increases. This is a documented molecular process. It is the reason alcohol is classified alongside tobacco rather than alongside substances that pose only behavioral or social risks. Now I want to address the blood-brain barrier specifically, because its integrity is crucial to everything I have described. Research has documented that chronic alcohol exposure increases the permeability of the blood-brain barrier. The tight junction proteins that normally create a selective seal between the bloodstream and the neural environment are degraded by repeated ethanol exposure. A more permeable blood-brain barrier means that substances which should be excluded from the brain can enter. Inflammatory molecules, metabolic toxins, and immune cells that are not supposed to cross into the neural environment can do so more easily. The protective system that is supposed to defend your brain is undermined by the same substance it is trying to filter. This matters because it creates a compounding mechanism. Early alcohol exposure damages the blood-brain barrier slightly. That damage allows slightly more acetaldehyde and inflammatory signals to enter the neural environment. That causes slightly more neuroinflammation and slightly more receptor adaptation. Over time, the mechanisms amplify each other. Each exposure leaves the brain marginally more vulnerable to the next exposure. The relationship between alcohol and neural damage is not simply linear. It has documented feedback dynamics. Let me now address the neuroadaptation that underlies physical dependence, because it connects the receptor pharmacology I described at the beginning with the severe medical risks at the end of the dependency spectrum. When the brain is repeatedly exposed to ethanol's pattern of enhanced GABA activity and suppressed NMDA activity, it adapts. This is what brains do. They are adaptation machines. The brain downregulates its sensitivity to GABA and upregulates its glutamate signaling in order to maintain its baseline functional equilibrium. This is called neuroadaptation, and it is measurable at the level of receptor density and sensitivity. The consequence of this adaptation is tolerance, the need for more alcohol to achieve the same subjective effect. But neuroadaptation is not merely a matter of subjective experience. The receptor level changes represent a genuine physiological restructuring. The brain has reconfigured itself to function with alcohol present. And when alcohol is suddenly removed from a brain that has undergone significant neuroadaptation, the compensatory upregulation of glutamate activity becomes unopposed. The brain that had been forced into balance by ethanol suppression suddenly finds its excitatory system overactive with nothing to counterbalance it. The clinical result is alcohol withdrawal syndrome. In mild forms, this means tremor, anxiety, and sleep disruption. In severe forms, it means grand mal seizures, delirium, and cardiovascular instability that can be fatal without medical intervention. Alcohol withdrawal is one of the very few substance withdrawal syndromes that carries a clinically significant mortality risk without medical management. Most withdrawal syndromes are uncomfortable. Alcohol withdrawal in a physically dependent individual can kill. This fact alone communicates something important about the depth of physiological change that repeated alcohol consumption produces in the brain. What does the totality of this evidence recommend? What does the neuroscience tell us about how to protect this extraordinary organ? The data taken in full does not support the existence of a completely safe level of regular alcohol consumption. The carcinogenicity evidence, the neuroimaging studies, the neuroinflammation research, the blood-brain barrier permeability findings, and the receptor pharmacology all point in the same direction. Every exposure has a cost. The cost may be small at low doses, but it is not zero, and the public has been given a very different message than the one the evidence supports. There is, however, documented capacity for partial recovery. Neuroplasticity is real. Studies examining individuals who stopped drinking after regular consumption have documented partial hippocampal volume recovery over sustained periods of abstinence. Some white matter integrity improvement has been measured. The brain does attempt to repair itself when the chemical insult is removed, but the recovery is partial, not complete. Not all structural damage reverses, and the window of neuroplasticity narrows progressively with age. The older the brain, the more limited its recovery from documented damage. What this means in practical terms is that timing matters. Earlier cessation produces better outcomes. The capacity for recovery is not unlimited, and it diminishes with each year of continued exposure and each year of advancing age. I spent my life believing that the most important obligation of anyone who understands something true is to communicate it clearly to those who have not yet encountered it. The documented neuroscience about ethanol and the brain is uncomfortable. It contradicts messages that billions of people have received from advertising, from physicians, from cultural traditions, and from their own experience of alcohol's pleasurable effects. But discomfort has never been a legitimate scientific argument against a finding. The evidence is what it is, regardless of whether it suits our preferences. The brain is the most complex structure identified anywhere in the known universe. It is not a metaphor to say this. In terms of the number of interacting components, the density of their connections, and the range of functions they produce, including consciousness itself, no structure we have found anywhere approaches the human brain in complexity. It deserves to be treated with the seriousness commensurate with that complexity. Understanding what documented neuroscience reveals about substances that alter and damage it is not a luxury. It is exactly the kind of knowledge that should be universal. If this science reached you today in a form you had not encountered before, subscribe to this channel. That is all I ask. I will continue bringing you the documented evidence about how to understand and protect the most extraordinary structure you own. The 3 pounds of neural tissue that generates every thought you have ever had, every memory you carry, every relationship you value, and the very capacity to understand what I am saying right now. The evidence is clear. The mechanisms are documented. And now you have them. I'm Albert Einstein, and the science does not negotiate with what we wish were true.